Okay, so again, we're going to be discussing Newton's second law, right? So, and now I'm going to write this as F is equal to mass times the second derivative of position. And in this case, position, we're going to denote it as R is equal to position instead of X that we did last time. So now, the derivative of position, again, is velocity, which we'll write as R with a dot on its head. Then the derivative of velocity is acceleration, which we'll describe as position with two dots, so the second derivative of position again. Now, to find the reason we did this is so we can easier understand Newton's second law in 3 dimensions. So let's just take position real quick, right? And we'll write position as, and we'll write, sorry, let me just erase that real quick. Okay, we'll write the vectors for it, the Cartesian coordinates for it. So now this will be x times x hat plus y times y hat plus, let me just fix that plus sign. You know what, let me just, okay, plus z times z hat, right? And these are unit vectors, so this, and this term right here, let me just fix that again, and this term right here, unit vectors, which are just equal to 1, right? So they're just equal to 1, they're just constants. Now, the reason this is important is, now if we derive this into acceleration, what we'll get is this is equal to, so acceleration, or the second derivative of position, is equal to the second derivative of position in the x direction times x hat plus the second derivative of position in the y direction times y hat plus the second derivative of z in the z direction. Oh, sorry, the second derivative of r in the y direction, the second derivative of r in the z direction times z hat. My mistake. And this here we have the three-dimensional vector system, or the three-dimensional Cartesian coordinates for the acceleration, right? And again, to understand this a bit easier, we could take this as being this. We could take that as being y, the y coordinate, or the y-axis. Sorry, and we could take this side as being the x-axis. And now this side comes out, and we can label this z, right? And we'll get back to this in a second. So now let's take force. Let's just take force alone. And of course you can't just take force alone, right? Because it's comprised of mass and acceleration. But if I were just to put a number here, you'd have to say, okay, force is equal to that. So if I put force here, just say, okay, yeah, force is equal to mass and acceleration, right? Just so we can understand better. So force, we can also divide like position and acceleration and velocity into 3 Cartesian coordinates. And the reason I wrote it like this, we'll understand in a second. So force we could write as force in the x direction times x hat plus force in the y direction times y hat plus force in the z direction times z hat, right? Okay, now that we have this, you know what, this is bothering me, let me just sketch this. Okay, now that we have this, the reason this helps us understand is now let's replace the force with the mass times the second derivative of position. And what I mean by that is, now force is equal to mass times, it's now going to be equal to the mass times second derivative of position in the x direction. Like, do you see? It's the acceleration in the x direction, and therefore we get the force in the x direction, right? Because mass is unchanging. Times x hat plus, not force, whoops, okay, times mass, let me just rewrite the m, times mass times the position, second derivative position in the y direction times y hat, so times y hat plus, that's a hat, times the mass, times the second derivative of position in the z direction. So times z hat. Okay, now that we got this, what this tells us is that force is equal to the second derivative of position times mass can be comprised of these three equations. So we can comprise this of three equations. Force in the x direction is equal to second derivative of x times mass. Force in the y direction is equal to second derivative of y, or the position in the y direction times mass. And force in the z direction is equal to second derivative of position in the z direction times mass. And what this tells us is that, and this is really cool because it tells us that Newton's third law is really, so Newton's third law in 3 dimensions is comprised of 3 one-dimensional equations. And that's really cool. So if I have a ball here, so let's say I have a string from the origin and then a ball here, for example, and here's the shadow of the ball. It kind of goes this way. And this is affected by Newton's second law. And there's a force applied to this, right? Let's just say there's a force applied to this. That force is being dispersed into 3 directions, specific to this situation over here. And so Newton's third law, in this case, for this ball, is really just 3 one-dimensional laws working together and are equivalent to this one equation. And yeah, we're finished. So Newton's, again, just to make sure and clarify, Newton's second law is equal to 3 one-dimensional equations. I was ready. 3 one-dimensional equations. So Newton's second law in 3 dimensions is equal to 3 one-dimensional equations.